Okay, so today we should move on. We already talked about section 6.5. We did 6.4 and 6.5. Do you have any questions? Okay. Try the homework. If you have issues or questions from homework, we can work on this together. So today, let's move on to section 7. This is another more theoretical session. Later chapters, in chapter 8 or 9, we focus more on the application, but now still trying to figure out what would be good for the estimation methods. S6.7. So it's another very theoretical section. The title is called Sufficient Statistic. It is similar to what we mentioned in 6.2 and 6.3. We have order statistic, and then here we're talking about sufficient statistic. So the word sufficient statistic is describing the statistic we're doing. Essentially, when the word statistic used singular, is mentioning one formula or another formula that we use to calculate about the underlying picture. So sufficient statistic is a terminology about some of the calculations. So let's look at how do we define sufficient statistic. The title really focus on how do we factor the likelihood function. So here, suppose we have a random variable. We have n random variable collected for a single distribution. Let's assume the joint distribution for them is f, x1, x2, xn theta. So this theta here is the parameter we're trying to estimate. So this section, the sufficient statistic, is connected to 6.4. We are trying to use a random sample to try to figure out a way to estimate the theta. So theta is kind of like a parameter that you knew that belong to your density function, belong to the distribution. And we're assuming that we could use x1, x2, xn to figure out the theta. Okay, so let's say we created this probability density function or probability mass function, assuming the x value are all the variables that we have, right? And then y equal to ux1, x2, xn is sufficient theta if and only if the function or the joint likelihood function can be factored into two functions. So the first one is the phi function. Phi is the one that has u as part of the component and also has theta. The other one is h. H does not have any theta. So then h only have the x value in there. So suppose the joint distribution or possibly the likelihood function can be factored into two parts. Part of it is related to theta. Part of it is not related to theta. In that case, we will call that suppose one of the factor depend on only on u. U would be the statistic we're talking about, and this part does not have u. If this is the case, then we would say that the formula ux1, x2, xn is sufficient. So we're able to factor into two parts. Part of it is the one that is related to theta, but in that one that related to theta, u is the only thing in there. So we don't have the individual x1, x2. U would be the one that would allow you to figure out theta, so to speak. I mean, the reason that we see that is a lot of times we would want to maximize the likelihood function here. The f in this page, it could be the joint distribution, which will be density function for x1 times density function for x2, and keep multiplying until multiplying the density of xn. So then the f in this page is almost like the likelihood function. If you want to try to find the maximum likelihood estimator, we'll be maximizing this function. How are we maximizing it? We're trying to maximize this function by choosing appropriate formula for theta. So now if this part are not related to theta at all, and therefore we'll be maximizing this part, and therefore you will be the only one affected theta. So this factorization idea, your likelihood function, you figure out a way to factor it. If we were able to factor this into two, one of them has this formula in there, then this one is what we call sufficient. So this idea of sufficient statistic really focus on how do we factor the likelihood function. Okay, so let's look at a couple of examples to see how different scenario, how do we determine the sufficient statistic, or what do we have to focus on in order to figure out the appropriate formula for theta. The first example is from Poisson distribution. I mean, we've done a lot of example exponential distribution or binomial distribution. Poisson distribution is this one. Okay, so if we go to Poisson distribution, we know the probability for Poisson distribution. Probability is lambda to the x power over x plus 2 e to the negative lambda. Now, assuming we have a random sample, that means we have n x value, x1, x2 till xn. So if we want to find a joint distribution, assuming those x values are independent from each other, that's what we call a random sample. Whenever you get a random sample from the same distribution, all these random variables are independent from each other. So because they're independent, you can take the individual probability and multiply them all. We have all this multiplied together. What we have in here, I colored in orange. Those are the individual probability multiplied all together. That's how we create a joint distribution. Joint distribution is actually a multiplication of all these. And the lambda to the x power can be joined together, become lambda to the summation of xi. The e to the negative lambda, we got n of them, so that's really e to the negative lambda raised to the power n, or e to the negative n lambda. The denominator is x factorial, but we have n, so we have x1 factorial, x2 factorial, and xn factorial. That is actually a big multiplication. So now we can see if we factor it and we focus on the theta, in this case, actually the lambda. For Poisson distribution, the parameter is the lambda. We're trying to figure out a way to say what is closely related to lambda in order to maximize this value. So now we end up getting, after combining the variable, we have lambda times lambda to the power n times x bar e to the negative n lambda, and now with 1 over factorial multiplied. So we can see on the far left in the factory, the one that's related to lambda is over here. These are all the terms related to lambda. And that one is related to lambda, another factor. And this is the h that we mentioned in the definition. You kind of factor into part of it is a factor, by factor we need multiplication. This h part is not related to theta, independent from theta. This part is affecting the value of theta. So in this case, over here, the 1 over the multiplication factorial is h, and then this part is lambda. It's related to lambda. So if you look at the one on the factor on the left, the only thing that really matters is x bar. So x lambda and x bar, that's what we have in here. The individual xi is no longer, it doesn't matter anymore. So we would say x bar would be a sufficient statistic for lambda, for if you want to determine lambda. Any question? Are you okay? So it looks like we're basically factoring the likelihood function in order to identify which part of the factor is connected to lambda, which part of the factor is not connected to lambda. So this is so in chart determination of sufficient statistic, it depends on how do we factor the likelihood function. So moving on, see here we have a normal distribution. I'm writing down the density function for a normal distribution. So if you have an individual xi, assuming that the variance equal to 1, that's 1 over 2 pi times the variance equal to 1, so that's just 1 over 2 pi. Assuming that we're trying to find out what was the mean. The mean is the only parameter here, e to the negative x minus mean square over 2, because variance one. So then we have multiplication of all these density function. And therefore, the joint distribution for all n variable will be a multiplication of all these. And then 1/2 pi, 1/2 pi, we got n factor of it. So that's 1/2 pi to the n power, or 1/2 pi to the n/2 power. That was this coefficient. The exponential part, we'll probably have to add the power. If we're adding this power, it's going to be a summation. So e to the -1/2 summation x minus xi. And then we're going to try to look at a factor that part of it is related to mu, part of it's not related to mu. Mu is a parameter in this, but it doesn't work out at first when you just look at this whole multiplication. Because individual mu is connected to xi, and we don't want it mu to be connected to xi. We want a mu to be connected with one thing. Individual xi is sporadic, so we're trying to get rid of that randomness to get one single formula to relate to mu. So what do? We enter the perceived sufficient statistic. So we enter x bar, and then here we have x bar minus mu, and here we have x minus x bar. Right, so then we separate them into two multiplication. This one is one that's related, connected to mu, and that factor is not connected to mu. But this one was actually related to the variance. Any question? So that was another example. It's a little bit artificial because the beginning of it we were not able to connect mu to x bar. That we kind of enter mu minus x bar, or x bar minus mu, and that's why we kind of separate minus mu plus mu there. So then the minus x bar plus x bar was artificially entered into the whole picture, and then separate that from e to a summation power is multiplication of the exponential function. We turn that into multiplication of two function in this factoring process. Any question? Okay. So identifying proper factoring here has some this is being created, and we felt like x bar should be something related to mu. That's why we kind of enter the x bar. X bar is artificially entered to the whole picture. Now, this example is the Bernoulli distribution. Bernoulli distribution is when we run something, there's only two outcomes, success or failure. So x equal to 0, suppose that would be the failure. If x equal to 0, the failure rate is 1 minus p, 1 minus 0, it's 1 minus p. X equal to 1, if x equal to 1, the 1 minus p goes away, and that's probability is p. So basically, the Bernoulli distribution success rate is p, failure rate is 1 minus p, and therefore for Bernoulli distribution, the only parameter is the probability p. If we're trying to find it out, I think we've done this before, in the max likelihood estimator method, we're going to take that probability for x1, x2, xn, we're going to multiply. As you see here, this is a joint distribution. P to the x1, 1 minus p to the 1 minus x1, and so on, and of the multiplied. So p to the summation of xi, 1 minus p to the n minus summation of xi. That's the same as we have in 6.4. This one, we don't have to try factoring because you can see that the only thing related to the value of p is the summation. So summation of xi would be a sufficient statistic. So then when you try to figure out the value for probability p, the only thing you should worry about is finding the summation of xi, because that's the only thing you might need for calculating p. It doesn't equal to p, but it's a major number that will be in the calculation of p. That's what we mean by sufficient statistic. Any question? Right, so this is the Bernoulli example explaining what will be the sufficient statistic, which will be the summation of xi in the case. All right, so here, the last one, we're trying to calculate the conditional probability. If y equal to a value, what will be the summation? How do we calculate the probability of x1 equal to x1, xn equal to xn? So this is one of those scenarios. What would that probability can be? How can we calculate that probability? Right, this is a conditional probability. So based on the conditional probability formula, the denominator is probability y equal to y. The numerator is individual probability, and because of independence, it can be calculated this way. The denominator is actually a binomial example. The denominator is having y success out of n trial. So we would have a probability, binomial probability in here is ncy p to the power y, 1 minus p to the power n minus y. Numerator is a pure Bernoulli probability. And then you can see many of the common factor will cancel. So then the only thing we left is 1 over ncy, that would be the. So this is saying that given the sufficient statistic y, if you have sufficient statistic y, we will be able to calculate this probability, the conditional probabilities. It depends on the NCY. Any question? So that would be the final condition. It doesn't depend on the parameter P anymore, just 1 over NCY if we already have y, meaning that y will be enough once you already know if you are calculating properly. Okay. So then you can see we've been doing a couple of examples on how to determine sufficient statistic. And people will be like, is there a faster way of determining sufficient statistic depending on each individual distribution? The answer is yes. So through all these examples, we realize they have a lot of similarity. That is, in order to identify the sufficient statistic, one of the things you can do is analyze the density function. So all density function can be analyzed into this form. Okay, the analyzation will be, you can turn this density function into exponential function. Then in the exponent, part of it will be multiplication of a function related to theta with a function related to x. Part of it will be a function only related to x, and part of it will be related only to theta. So it's 3 different factors. For example, the first question was a Poisson distribution. Poisson distribution, the probability e to the negative lambda to the power x over x factorial. So we can analyze it into exponential form. And this on the board is already analyzed. But since here we are, any function can be written into exponential function. Originally, it was e to the negative lambda, lambda to the power x, which is also exponential. And then there's an x factorial. So how do we write it into exponential function? This part is already exponential, e to the negative lambda. This part, you want to write it into exponential. You would use the inverse, right? The inverse exponential function will be natural log. Okay, and then the natural log, when you can move the power to the front. So that's the second one, turned it into exponential function. Now this one, it is actually x to the factorial to the -1 power. We can write that into e to the natural log of x factorial take -1 power. So what happened is you can move the -1 power to over here to the front. Yeah, so that's what we have. And then all you have to do is this is actually e to the negative lambda plus x natural log lambda, and then minus the natural log of x factorial there. So then this is now exponential. So all we have is focus on the exponent. This is a parameter. So this is the parameter times the variable. This is only related to the variable. This is only related to the parameter, right? Right? So if you look at all density function, you can always analyze into 3 different scenarios in the exponent. So in the exponent is function x function times theta function plus x function plus a theta function. So you can kind of look at them into 3 different parts. The second scenario is a normal distribution. The normal distribution is 1 over √2 pi times e to the negative x minus mu squared over 2. We again analyze that into 3 parts. Like, it's already expanded, but if we were expanding it ourselves, it would look like this. And maybe I should write on the computer since we wish to recorded. So this one, how do we know that it is that way? Being able to analyze into three part in the exponent helps in terms of determining the sufficient statistic. So this one, the original formatting of the normal distribution is this. When you try to analyze the first one, it's not exponential, so we turn it into exponential. So you go e to the natural log, that's turn everything to log into exponential, then the 1 over 2 pi. Okay, and that part is already exponential, so you go e to the negative and then x minus mu squared over 2. So that means this is the exponential, so it's exp, right? In the exponent is what we have in here, and you move the negative. The negative 1 over, the 1 over is actually negative 1 power. So you have negative 1, and there's a 1/2 power in the root. 1/2 power also goes to the front. So negative 1/2, and then you have natural log of 2 pi. Right, over here, you would expand that square. If you expand the square, you get x squared plus 2 mu x plus mu squared. And then there's a negative in the front, which affected every single term. So it would be negative x squared over 2, and then negative this one over that 2. The 2 will cancel. So negative mu x. Oh, there was a negative sign. So this was negative, so that one was negative. So this one was positive. Negative is positive. And then last one was a negative mu squared over 2. So then analyzing each part, we're able to tell why it looked like this. So we got positive x mu. That's the only one that had multiplication of the variable and the parameter. This is an x function. That was a number. That was a number. So these are that was a mu, right? This is a mu function. This is the x function. So we're able to analyze it into exponential function. In the exponent is a parameter function, time variable function, only variable function, and only parameter function. Are we okay? So why are we doing this? Because after we analyze the density function, we realize that there are sufficient statistics. It is only related to the one that involves multiplication of the parameter and the x. So, for example, the first example being the Poisson distribution, what was the sufficient statistic? It was the summation of the x. Summation of x, right? Summation of x with the x bar. But summation of x divided by n will be, that one is a sufficient statistic. So the second scenario, you look at the one that actually multiply your parameter function. For the second example, the normal distribution, the parameter is mu. And you can see x by itself or mu by itself is not going to be the sufficient statistic. The sufficient statistic is the one that multiply your parameter, in this case with the x. And the summation of x will be the sufficient statistic. So to be the sufficient statistic, you have to add its summation. Now, for the last one, with the vanilla example, again, originally it was not exponential. If you make it into exponential, you have to add a natural log. So e to the natural log, p to the x to the front, and e to the natural log, 1 minus p, 1 minus x power to the front. So after combining the like term, then we realize the one that's multiplying the parameter. That was a parameter by itself. This is multiplying the parameter. Summation of x is also sufficient for the last scenario. So then we can see that we don't have to do the likelihood function anymore. If you want to use a factor theorem definition, you have to create a big multiplication, a big likelihood function, and factor it properly. But this idea is that maybe we don't have to pick the density and do a big multiplication of the density. Maybe we can just focus on the density and analyze it into exponential form. In that power of the exponential form, we focus on the one multiplying the parameter function. That one, summation of that one will be a sufficient statistic. So we would have this result saying, so that was a theorem saying that suppose we can analyze the probability function or the density function into exponential form. In a power, you may have a parameter function time the variable function summation of the kx. So if the exponent has kx times p theta, then summation of the kx is a sufficient statistic. And that's so that's a common theme in all the examples that we've done. So we generalize from that idea to get a better way to find sufficient statistic. Any question? Are you okay? Any question? All right, so that's the idea of how to find sufficient statistic faster. All right, so we're going to do one more example. Let's go back to exponential distribution. The density function for exponential distribution is 1 over theta e to the negative x over theta. That was the original density function. We have part of it that's already exponential. It's the negative x over theta. And part of it is 1 over theta. If you want to write it into exponential form, it will be e to the natural log of 1 over theta. Okay, so 1 over theta is actually theta to the negative 1 power. You bring the negative 1 to the front, so e to the negative natural log of theta. That's what it is. It's a multiplication relation. So rewriting that one into e to the negative natural log of theta, and then combine with e to the negative x over theta, we have this. All right, again in the exponent, e to the whole thing. EXP is really another way to write exponential function with base e. And you see a multiplication here, and that one is a standalone by itself, a theta function. We focus on the multiplication. This is a theta function, the x is multiplying. So the x summation of x will be the kx equal to x, so summation of x will be the sufficient statistic based on the theorem that we just mentioned. Any question? Are you okay? Factoring. So analyzing the density function, turn it into a total exponential function, and in the exponent, we're able to find what will be the key. But remember to add a summation to it, because sufficient statistics is supposed to be combining. So we're not talking about one single x value. We're talking about summation of all the x values. Whatever that one is, you want to summation. You want to have a summation over it. That was the sufficient statistic. As we mentioned, I've been talking about likelihood function, even though we're talking about sufficient statistics. That kind of shows a lot of connection and similarity between the maximal likelihood estimator and the sufficient statistic. But one thing we can see is that the sufficient statistic is not unique, but maximal likelihood estimator is supposed to be unique. But what we can see is that after talking about the sufficient statistic, there may be several sufficient statistics, but the maximal likelihood estimator actually is a function of a sufficient statistic. So the sufficient statistic might not be your maximal likelihood estimator, may not be the right way to do the calculation, but you do some algebra on the sufficient statistic, it will give you the estimator that we should have. Right, so what we want to do is actually combine the two. The maximum likelihood estimator normally is the maximizing your likelihood function. So in a sense, it's a good estimator. But then if we are capable of making it also a function of sufficient statistic, that will lower the, I think it will lower the variance, will make it better. So here is just connecting the maximum likelihood estimator with our sufficient statistic talking about. And here, this is kind of part of the reason that if you have a likelihood function analyzed into a multiplication, since we wish to maximize the likelihood function, and this one does not connect to theta whatsoever, you can't really maximizing that and factoring the theta. So then the only one we should be maximizing is a function phi. One of the factor is a key when you try to find theta, and the other one is unrelated. So being able to factor properly could also make your maximization easier. We can identify the maximum likelihood if we can identify the sufficient statistic. Anyway, now this is expanding the idea. In the previous pages, it was only one parameter, that will be this theta. And here we're talking about what if you want to estimate not just one parameter. So remember, in the normal distribution, we have mu that we want to estimate. The variance we're assuming equal to 1, because at the beginning we don't want to start out with too many parameters. But realistically, sometimes we do have multiple parameters to estimate, so now we maybe need more than just one sufficient statistic. So here we are. Suppose we have two parameters, theta 1 and theta 2, that we need to estimate. What would be a sufficient statistic for two parameters? So understand this. So then the idea would be, if you want to estimate two parameters, you're going to need two sufficient statistics, at least two statistics. So what do we do? Again, you want to create the likelihood function, and again, you want to factor the likelihood function. So part of it is independent from theta 1, theta 2. Part of it is dependent. So H is independent. Theta 1, theta 2 is related to our underlying sufficient statistic. So if you can summarize or combine things into the way that there's only two functions that you need in order to connect to theta 1, theta 2, these two functions, the U1, U2, are being called jointly sufficient statistic for the parameter theta 1, theta 2. Any question? So this page is extending the idea of sufficient statistics to two parameter compared to one parameter example. Any question? So I'm going to use an example to illustrate the point. Normal distribution is the most common one that has two parameters. We have the mean and we have the variance. The last example, when we talk about normal distribution, we're assuming we're only estimating the mean. We're assuming the variance equal to 1. More realistically, we would end up have to have sample from a same normal distribution we're estimating both. We need to find out what was the variance and what was the mean. So theta 1 is a mean, theta 2 is the variance. In that case, the calculation of the density is this. Then we have to multiply n of them. So we have these all multiplied. Multiplication of exponential function will be summation of the n the exponent. So this is e to this, and there's n of these multiplied. That's why we end up getting this. There's a summation in the exponents. And again, we're trying to find what would be necessary. We can expand the power there. After you expand, you have a summation of xi squared. We also have a summation of 2 times x1, x and theta 1. So summation of xi squared and summation of x, those are the two that are probably related to the theta 1, theta 2. On the other hand, so after combining that like term, expanding the summation of square, get this. So we could factor this into 2. Actually, we didn't factor at all with multiplication of 1. So there's no independent term. All of them are related to either one of these two summations. So y1, which equal to summation of xi, that's the empirical second moment. Now y2, which is the summation of xi. It's not a second moment, right? We have to divide it by n to be the second moment. So x bar will be the first moment. X bar is summation of xi divided by n. And then if you take the y1 minus the y2 squared over n, this is a calculation of the sample variance. So these two are what we consider sufficient. I mean, so both y1 and y2 is a pair of sufficient statistic for theta 1, theta 2, or you can use the sample mean and sample variance as a pair. Those pair is also sufficient. So both of these two are okay. So yeah, what are sufficient statistic for parameters theta 1, theta 2? Any question? So this will be an example when we are estimating two parameters at the same time using sufficient statistic. All right, so why are we talking about sufficient statistics, and why would this section be meaningful or useful? Right. So the reason it's called sufficient statistic is once the statistics, like the summation of the xi is given, then if you want to estimating lambda or the Bernoulli portion p, that's all you need. You don't need any other information. You don't need to know what is x1, what is x2, what is x3. You only need to know the total summation of them. So once the sufficient statistic is given and we don't need additional information, and that's why it's called sufficient statistics. Okay, so this is kind of the reason why we want to know what's sufficient about our estimate. Okay, another thing is relation between the unbiased estimator and sufficient statistic. Unbiased estimator is when the expectation of statistic equal to the parameter. So we certainly wish to have any estimator that we're using, we want it to be an unbiased estimator. Now here we have a result saying, suppose you have a density function that y1 is sufficient statistic and y2 is an unbiased estimator. So maybe we can find a way to combine these two properties and make it better. So what do we do? Maybe the one that's unbiased, y2, is not sufficient. So by itself is not sufficient. So what do? We can find a conditional expectation of y2 given y1. Okay, and because it's a condition on y1, so it's a formula of y1, which will be a formula of the the sufficient statistic, which makes it itself a sufficient. So if you have a sufficient statistic, a function of sufficient statistic would also be sufficient statistic. So u y1 is also sufficient. On the other hand, the explanation of y2 given y1, because the condition it's originally a conditional expectation. Since y1 is unbiased, so the expectation of y2 would equal to theta. So therefore, when you do this, expectation of this new number, this mu y1, will also be the underlying parameter. So the fact that y2 is unbiased, it causes the result that conditional expectation y2 given y1 is also unbiased. So we're creating this new function, the uy1. It is both unbiased and it's sufficient because it's a function of y1. It's also sufficient. So that's kind of the reasoning on how to create a estimator that is both sufficient and unbiased. Any question? So that was one of the idea. If you ask how do we find a conditional expectation, all expectations should be calculated. In the discrete version will be added all together divided by n. In the continuous version will be the integration process. So realistically, if we have a theta, we probably averaging process. All right, this is the proof of what we have here. In order to prove it, we really are trying to prove two things. Number one, we want to prove this is unbiased, and that can be calculated by taking expectation of this, which you put y2. Number two, we want to prove it's sufficient. I think u y1 is a function of y1, and y1 is sufficient. U1 certainly is also sufficient. The only thing that would be a little bit hard to prove is we see the variance of it is less than y2. y2 is a unbiased estimator, but when there may be several unbiased estimator, which one is better? It's the one that has smaller variance. So then one of the other benefit of this process is we're able to create an estimator that has smaller variance. And it's about time. All right, this is a mathematical proof, which would be one is the expectation calculation, one is a variance calculation. So we can show that the variance, it is smaller than the original variance. That'll be basically the idea of the proof. That's it for today. Thank you. Any questions? All right, you can see it's quite theoretical, but I think it's still meaningful when we are doing discussion or just writing a method. Sometimes we will be taken away by the individual calculation, but rechecking if it's biased or if it's sufficient will be kind of helpful to lead it back to the right way. I guess I'll see you next Monday.